Now, this final section of this chapter is related to the frames and machines. The mechanical analysis related to frames and machines are being derived based from the principle of the structural study. So, frames and machines are structural features assembled from multiple components or members which are subjected to multiple force, meaning it may have more than two forces. So, frames are normally used to support loads, whereas machines, it contains moving parts and it is designed to transmit and alter the effect of load. Okay, now let us look at few examples on how we can construct the free body diagram on the structure of frames or machines. Okay, so if you look at this particular example, this is a kind of a frame and you are required to draw the free body diagram of each member. Okay, if you want to draw the free body diagram on each member, first you have to identify all the supporting reaction forces at each joint. Okay, so you know joint A is a pin type of joint, so supposedly there will be two reaction forces in the Y and also in the X direction. The same goes with joint C. It's a pin type of joint, so there should be two reaction forces in the Y and also in the X direction. Now, if you want to draw the free body diagram of each member, then you have to separate the truss member or the frame member into an individual components. So as you can see, there are two members of this particular frame, which is member AB and also member BC. At member AB, there is an external moment acting on it, whereas at member BC, there is a vertical force of P acting on it. Okay, now at joint A, you know there is a vertical force of AY and also horizontal force of AX, whereas at joint C, there is a vertical force of CY and there is a horizontal force of CX acting on it. Okay, now look very carefully at joint B. Joint B is actually interconnected with a pin. So if you recall from the method of joints, for a pin connected type of joints, there will be two reactive forces, which is the vertical direction and also the horizontal direction. So if at one side, the horizontal direction of BX is pointed to the right, and then at the other member, it should be pointed on the opposite direction, so that it reach an equilibrium state. Okay, so accordingly, if there is a vertical force of BY at one member, it is pointed upward. On the other member, it will be pointed downward at the opposite side. So this is a concept of couple forces acting at joint B, which is assumed to be pin connected type of joint. As for the second part of the question, you are required to draw the free body diagram at pin B. So if you want to draw the free body diagram at pin B, this is very similar to the method of joints. Okay, joint B or pin B is connected to member BC. So there is a reaction force between joint B and member BC, and we are going to call it FBC. Accordingly, joint B is also connected to member AB. So there should be a reaction force between joint B and member BA. So I'm going to call that force to be FBA. So if I were to redraw the free body diagram over here, this would be pin B. This is the reaction force between member BC and this is a reaction force between member BA. Okay, if I were to resolve the sengat-bengat forces into an equivalent X and Y direction along the vertical side, this would be the FBA in the Y direction and this would be the force of BA in the X direction. Okay, accordingly, if we resolve the FBC into an equivalent X and Y direction, this would be the direction of FBC in the X direction and this would be the direction of FBC in the Y direction. Okay, so that is the free body diagram, particularly at joint B. It's done. Okay, now the final part of the question asks you to draw the free body diagram if the two members are connected together. So basically, you are redrawing the diagram that I showed earlier, okay? Okay, there are two members, AB and also member BC, which are connected together. It looks like this. So you know there is a vertical force of P acting on member BC and there is a moment acting on member AB. Okay, at joint A, it's a pin connected type of joint, so there is a vertical force of AY and also horizontal force of AX acting on it, whereas on the joint C, there is a vertical force of CY and horizontal force of CX acting on it. Okay, that's done. Itu saja. Now, in the second example, it is actually a diagram of a frame connected to pulley, which is connected to the cords. Okay, so in the first part of the question, if you are to draw the free body diagram of the entire frame, including the pulley and the cords, so basically it's like a basic free body diagram that you normally draw previously. So you know at joint A is a pin type of joint, so there should be two forces acting on it, which is the vertical force of AY and also the horizontal force of AX. And then at joint D, this is actually a tension caused by the cord. So you can just draw the direction of the tension force following the direction of the cord like this. Okay, so you are done for part A. As for the second question, you are required to draw the frame only without the pulley and the cords. So the highlighted region over here is the diagram of the frame. So if I were to redraw the frame, it would look something like this. So if you notice at this point of the frame, a cord is connected to it and the magnitude of the tension force is 500 Newton. Okay, so you can redraw the direction of the force caused by the cord like this, and the magnitude is 500 Newton. So at this particular point, the frame is connected to a pulley, and if you notice, this pulley is pin connected to the frame. Okay, so for a pin type of connection, the pulley cannot move in either X or the Y direction. So therefore, there is a reaction force at point B in the vertical direction. We are going to call it BY, and also in the horizontal direction, and we are going to call it BX. Okay, so what else is connected to the frame? So if you look carefully, there is a cord connected to this frame, and the magnitude of the cord, we call it TD. So accordingly, direction of the force caused by the cord can be redrawn like this. Okay, now next item at the frame is point C. So similarly, point C is pin connected to the pulley. So accordingly, there should be one vertical force at point C, we're going to call it CY, and also one horizontal force at point C, we're going to call it CX. Okay, and finally, the frame is connected at point A kan, so sama juga, A is pin connected, so there should be a vertical force of AY and horizontal force of AX. Okay, so that is all the forces acting on the frame. Okay, now the final part of the question asks you to draw the free body diagram at each of the pulley. Okay, there are two pulleys in this diagram, which is pulley at point B and also another pulley at point C. So if I were to redraw the pulley at point B like this is the middle point, the pin connected pulley. The tips here is, if you look at the free body diagram of the frame that you drawn here, so basically the direction of the forces should be opposite to the one that you have defined at the frame. Okay, so if BX is pointed to the left, accordingly at the pulley, the BX should be pointed to the right. Okay, so if in the frame the BY is pointed upward, then at the pulley the BY is pointed downward. It's like a couple force, very simple. Okay, now, the pulley is connected with a cord. So anything connected to it, you have to define it with a direction of force. Okay, so the cord can be represented in the free body diagram of the pulley like this. Okay, there will be one tension over here with the magnitude of 500 Newton, and there will also be another tension over here with the magnitude of 500 Newton. Okay, so that is the free body diagram at pulley B. Now we will apply the same concept in drawing the free body diagram at pulley C. So if this is pulley C and this is point C, so if you refer to the direction of the forces on the frame, so if the CY on the frame is pointed upward, then the CY on the pulley should be pointed downward. So accordingly, if the CX on the frame is pointed to the right, then the CX on the frame should be pointed to the left. Okay, so if you look carefully, this pulley C is also connected, okay, with the cord. Okay, so sama juga macam step sebelum ni, there should be a tension force at this point, and also there should be another tension force at this point caused by the cord. Okay, so dah siap. Okay, now this example is quite interesting. You are required to draw the free body diagram of the backhoe as shown. So the backhoe is more realistic. You see this almost everywhere at the construction site. So anyway, I just want to give a brief idea on how you can draw the free body diagram of the entire structure of the backhoe, and also just some example on how you can draw the free body diagram at each members. Okay, so if you look carefully at this backhoe, the member AB, member BC, and also member BE of this particular backhoe is actually a two-force member. So if it is a two-force member, then we assume that there is a force at each end of the member, okay, and the magnitude of the force is the same, and the direction, only the direction of the force is in the opposite direction. Okay, it's like a couple force. So if I were to redraw the free body diagram of the backhoe of this entire structure, okay, so I know the bucket and its content have a weight of W, so this W is acting downward like this, okay, and then this member of the backhoe is connected to another member called F, so I'm going to call this force acting at this particular member to be FF, okay, and this backhoe is also connected to another member called HI. Okay, so again, similarly, I'm going to call the force acting at this particular member to be FHI. So that's how you draw the free body diagram of the entire structure of a backhoe. Okay, just as a quick example, let me redraw the free body diagram of only the bucket member of this backhoe. So this is a profile of the bucket. Okay, I'm redrawing the profile, and I know that the bucket have a weight of W acting at the center of the bucket, which is at point G. So this W is pointed downward. This bucket is also connected at another member at point D. So as long as it is connected to another member, there should be a reaction force at that particular point. So we are not sure whether this member is a perfect vertical kind of member, so let's just assume that it is not that vertical direction. So therefore the reaction force at point D should have two directional forces, which is in the vertical direction, we'll call it dy, and also dx. Okay, so this bucket is also connected to another member at point A. Okay, accordingly member AB is not perfectly a horizontal kind of member, so therefore we have to resolve it into an equivalent AX value and also AY direction. So that is how you draw the free body diagram of individual members of frames or machines. Okay, now let's look at the final example on drawing the free body diagram of a machine. So this is a can crusher. This can crusher consists of multiple members, which is member EBD and also member AB and also the piston D. Okay, so if we are to consider the entire structure, entire can crusher, so we know at point A it is a pin type of joint. So supposedly there are two reaction forces acting at point A, which is AY and also AX. So accordingly, joint D is connected to the piston. So this piston cannot move vertically, kan? If it cannot move vertically, it means there is a reaction force over there. So we are going to call that vertical force as N. At the same time, the piston are pressing against the can to crush it. So by right, there is like some kind of force acting in that particular direction, and we are going to call the force over there P. Okay, so the direction is not important. Yang penting is how you define it, because at the end of the day, you will know the actual direction based on the calculation. Okay, now if I were to analyze and draw the free body diagram of this can crusher based on each individual members, then I have to redraw every individual member separately. Okay, so that is one member over here, which is member AB, another long member over here, which is member EBD, and also another member over here, which is the piston, which is used to crush a can. Okay, now let's label the member accordingly. So this is joint A, this is joint B. Okay, at this long member, joint B is over here, joint D is over here, and this D is connected to the piston over here. So at the end of this long member is joint E. Okay, now you know the support reaction at joint A is there is an AY over here and another horizontal force of AX over here. Okay, now if you look at point B is connected to another member. So we are going to call the reaction force at point B as FAB as it is connected to member AB. So accordingly, the point B at the other end of the member should be in the same magnitude with the opposite direction. Okay, so at point D, we are not sure the direction of the forces, so we are just going to consider it as a pin connected type of joint. So there is one vertical force over here, we're going to call it dy, and or a horizontal force over here, we're going to call it dx. Okay, okay, at the piston over here, it will have a couple force which correspond to the point D at another joint. So if the dx at one member is pointed to the right, then the dx at the piston should be pointed to the left. Okay, so accordingly in the vertical direction, if dy in one member is pointed upward, then the dy in the piston should be pointed downward. It should complement one another. Okay, finally at joint E, there is a force of 800 Newton acting towards the member. So you just draw it as it is, and then you know the angle over here is 90 degree, and that's it. That's how you draw the free body diagram of each individual members of the can crusher. Okay, let's see up.